My sound is not coming through. Okay, I will redo it. I'm glad that we have only, spent 3 minutes on this slide. So I'm saying, okay, now it's working. For the conversion between virtual address to physical address, we'll have a page table sitting in the main memory, and this page table has all the translations between virtual address to physical address. And in this example, we have 16-bit address, 4 kilobyte page size. So that's 12 bits for the page offset. We have the upper 4 bits, which is 1 hexadecimal digit for the page number, right? And then we're translating the virtual page number to the physical one by finding the 7th index in the page table, right? The page table is as big as the number of the different combinations of page numbers. So we have 16 entries. We're looking for the 7th entry, and then the number in hexadecimal over there is 9. So we're replacing 7 with 9 and concatenate it with the page offset, which doesn't change between virtual address and physical address. And then once we have done the concatenation, we have the physical address. All right, so there really, this basic scheme is pretty straightforward, but there are 2 problems we need to solve, and these are the 2 main topics we covered in lecture. The first challenge is that, if we're dealing with a big address, right, but we have a relatively small page size, then we'll have too many page numbers to translate, right? So for example, if we have a 64-bit address, still 4 kilobyte page number, 2 to 12, all of the upper 52 bits will be used for translation, right? And to do that translation using a single level page table, we need to have 2 to the 52 entries times 8 bytes per entry. So that is, a crazy amount of space in main memory. I don't think anyone has that much space in main memory in the world, right? A few petabytes. That's crazily big. And the solution to this problem is multi-level page tables. All right. So again, I'm changing the number a little bit so that I can have a small example to illustrate. 16-bit address, 256 byte page size. So 8 bits for page offset, 8 bits for page number. All right. And the way we do lookup is, we have quite a few page tables in the main memory. One of them is a first level page table, and the other of them are second level page tables. So as you can see, what I have in the first level page table is a bunch of addresses, right? So this is a 16-bit address machine. So each address is represented by 16 bits. And what I have is at each second level page table, I will have another kind of array of elements indicating the actual physical address, the physical page number. All right. So the way I do translation is, the first level page table can be looked up using a 4-bit number. I will use the upper 4 bits, right, to index into the first level page table. And what I have over there is the page table I should look at on the second level, the address for that page table, which is 2121. So, among the second level page tables, I will go to address 2121. And over there, I will see another page table that allows me to do lookup using another 4 bits from the page number, from the virtual page number, and to actually translate the whole upper 8 bits into the 8 bits for the physical address, the physical page number. All right. So to sum it up, first level page table has a bunch of addresses for second level page tables, and this can continue to have the third level or fourth level, etc. But eventually, at the leaf level, you will have a page table that does translation for the physical address, the physical page number. And again, you just take the physical page number F9, concatenate it with the page offset A6, you get the physical address. All right. So this is the first challenge. If we have a single level page table, the page table will be so big. But when we have multiple levels of page table, you see some of these pages are not on the disk, right? And you really don't need to spend that much time. Let's say for the disk entry over here, for the first level page table, you don't even need to allocate space in the memory for the second level page table, right? And that saves you a lot of space. All right, that's the relatively easy problem. The harder problem is that the translation is too slow, right? You remember whenever we need to access main memory, it takes hundreds of cycles. All right. And to solve this problem, the solution is a buffer, right? Whenever we see this kind of problem, a lot of traffic to the main memory, the most intuitive solution is to use a buffer for that, right? We have cache for the data in the memory. We also have translation Lookaside buffer for this translation table in the memory, right? So between the core and the memory, we add a buffer. And this buffer will store some of the more recently used translations, right? And the speed of the buffer is probably the same as, cache. So it's pretty fast, and usually it's fully associative so that we can maximize, the space that we're allowed to have on the TLB to avoid the traffic to main memory. So this is small, but really fast. All right. So, all right, here's essentially the question one of the homework, right? We give you some specifications about the size of the address, 16 bits, the page size, and we also tell you, this kind of organization, how many entries do I have in the translation Lookaside buffer? And we give you, a sequence of addresses, and we ask you to analyze, which of them is a hit, which is a miss, when page fault happens. I'll get to that. I get to the page fault in a second. All right. So suppose this is how my computer architecture looks like. We have 2 entries in the translation Lookaside buffer, and it's fully associative, so the order doesn't matter. All right. And because the size of the TLB is much smaller than the real page table, we need tag, right? It is tag that allows us to differentiate different blocks, or in this case, different pages. Right. So the first address, 7186. All of these numbers in the table, in the TLB, in the address, those are all in hexadecimal. So first thing I would do is I will look into the TLB, right? Nothing's in the TLB, so I don't know what to translate 7 into. So I need to go to the page table in main memory, and I find at index 7, so 0, 1, 2, 3, 4, 5, 6, 7, the number over there is 9, right? So I know I need to translate a virtual page number of 7 to physical page number of 9. So I will bring that entry into the TLB, right? The TLB will store this translation. If tag is 7, right, I'll search for the TLB using the virtual address, right? So if my virtual address has a tag of 7, the translation should be 9. All right. So this was a TLB miss, and then after that, we brought the translation from the main memory into the TLB buffer. All right. So let's have a look at another access. So this address is starts with an A. So the virtual page number is A, which is 10 in decimal, right? And again, first I want to look into the TLB. It's not in the TLB, so I'll go to the main memory. And at index 10, the translation gives us an F, which is 15 in decimal, right? So I know I need to replace A with F in the physical address. And again, I will store this translation in the TLB. Right? At this point, the TLB is filled up. So if I need another translation at a later point, some of these entries need to be thrown away. And then another virtual address, the address has a virtual page number of 7, right? And I'll look into the TLB, and tag of 7 is over there. So the translation can be done right away through the TLB without needing to go to the memory, right? So I'll just grab the 9 from the TLB. That is the physical page number. Do the concatenation. This is a TLB hit, right? So this is a very fast operation. We don't need to go to the main memory, right? The translation is available in the buffer. And now, yeah.
So I guess it's not going to really matter for the assignment. So I guess it's not going to really matter for the assignment, but I guess I'm just trying to think of, so when we try to access the TLB, search for the tag, it's not in there. We miss and we go to the main memory in the page table, to basically put it back. Then we rerun the instruction, right? Like that's how the TLB actually works in practice.
We rerun the instruction. Well, we continue running it from the new entries that just got populated in TLB. Just like when you access a data memory, right? You have a cache miss, you go to the main memory, you put it back into the cache, and then you continue from the cache.
Yeah, exactly.
Yes.
Okay.
Yes.
Awesome.
All right. So now it's a little bit more of a tricky example, right? So we're trying to access this particular virtual address, virtual page number of 2. It's not in the TLB, right? So I need to go to the main memory to find the page table, and at index 2, I think disk. What does it mean?
Gotta fetch it from the disk.
You gotta fetch it from the disk. The page is not in the memory, right? It hasn't received the allocation in the memory. So really, at this point, we can call it a TLB miss, right? First, we have a TLB miss, and then we also have a page fault. This is what we call a page fault. The page not in the main memory. And we need to spend, well, the memory has a latency of a few hundred cycles, maybe like 1,000 or at that magnitude. The disk has a latency of, I would say, like a few million cycles, right? Like 50 million, 100 million is not uncommon. So this will incur a very high latency. So at this point, it's really up to the operating system to decide what to do, right? Do we wait for this memory? Do we wait for this page? Or do we continue and then come back for it later? So that is, more like the operating system question, right? There's so many different choices you can take. And what we assume, for simplicity is that we're just gonna like wait. We'll grab the whole page from the main memory, put it, from the disk, and then put it in the main memory. And we're gonna update page table indicating, where did I put this new page in the main memory, right? And of course, this has to be an unused physical page number, like unused section of the main memory. All right. So once we have done that, we have already moved the page from disk to the main memory. Then we can continue with the standard operation where we do the lookup in the page table. Well, now it's in the page table, right? 2 gets translated to 7 for the physical page number. And then I also need to update my TLB. This is the most recently accessed one. So I will replace the older one, which is A to F, with 2 to 7. All right. So what we have seen over in this example is first, originally we have a TLB miss, right? 2 is not in the TLB. And then we go to the main memory. We find that 2 corresponds to a disk, right? It's not in the memory. So that's a page fault. And then we load the page from memory, the disk to memory. And finally, we update the TLB according to this most recently used translation. All right. So this is all the scenarios that you could encounter for TLB and page table access. So we have seen TLB hit, we have seen TLB miss, and we have seen TLB miss together with page fault. All right. So actually, I think in the rare event, you could have a TLB hit followed by, but at the same time, it's a page fault. That would be a very rare but possible scenario where the memory, well, of course, this is much larger than the memory. So some pages in the main memory could be evicted to the disk. But if we really didn't use TLB that much, this evicted page could still sit in the TLB. At that point, we'll have a hit in the TLB, but eventually when we use the physical address in the memory hierarchy, through cache, through the data memory, then we need to, the operating system will still catch it and then delay the whole operation. That is rare, but that could happen. Yeah.
So I think if I remember from 120, at least in one of the implementations, when you evict from the page table to write to the swap space, you would update the TLB at that point.
That would be one quite reasonable way to handle it, right? We just mark that line as 30, right? Not allow anyone to use the TLB. That's another solution, right? I guess it really depends on the exact microarchitecture, right? Different computers, different operating systems could have different design. They'll take different design options, right? But don't really worry about it. Most of the examples, if not all, will be either hit or miss and page fault. All right. So any questions from the online guys? We only have like one guy online, and we're preparing the whole setup, the camera, everything for him. The camera is only for you. You see, it's now recorded. So All right, if not, I'm gonna continue, right? So what we have seen so far is the basic page table and two challenges, right? It's too big and too slow. To solve the capacity issue, we use multi-level page table. To solve the speed issue, we use a buffer, right, the TLB. Now, suppose we already figured out how to do the translation, eventually we need to access a memory, right? So the next question is, how do we use the TLB in the cache hierarchy, right? A straightforward solution would be, well, the straightforward solution would be we first do the translation, right, to get a physical address, and then we'll use the physical address just like we have seen everything so far. We use that to index into the cache to compare tag, and then if it's a miss, we go to a memory, right? This is a very straightforward solution. TLB happens before the cache hierarchy, so it doesn't impact the way we normally analyze the cache. The problem over here is that this is a little bit slower than some of the alternatives. This is not really too slow. It's just a little bit slower than other options. And the issue is, well, we need to see the other side of the story, right? This is a physical cache. We do the physical translation and we use that to access the cache. The opposite technique is we first access the cache and then we do the translation. This is an entirely virtual cache, right? The cache is only accessed using virtual addresses, virtual tag, virtual index. And this is faster than the previous option. And that is because if we have a cache hit, right? If we have a cache hit in this organization, then we don't need to do the translation. We're saving ourselves that translation step. All right. Whereas in the previous example, well, regardless of whether it's a cache hit or cache miss, we need to do the translation first. And that could take a long time if it's a TLB miss, right? So by putting the cache lookup earlier in the process, we're able to save a lot of time, a bit of time maybe. I don't know the exact magnitude, but we're having some saving. But this will not work. There's a problem with virtual cache. Does anyone remember what the problem is? I think this sounds like a brilliant idea, right? But what's the catch? Yeah, let's pass the microphone.
Different processes might use the same virtual memory.
Yeah, exactly. Different processes might use the same virtual address. Very nice. So remember, in the example, we have 4 different processes. They're using the same address, but they really should translate to different physical address, right? If we use a virtual cache in that scenario, all of these 4 processes are going to use the same entry from the cache, whereas they should use different entries from the main memory, right? So, it's not going to work correctly if you just have virtual cache with multiple processes. All right. So this is when people come up with brilliant ideas, right? The problem with physical cache is that the TLB is located on the critical path. We need to do it before the cache. And the ultimate solution would be we have a virtually indexed and physically tagged cache, where we let L1 cache and the TLB operate simultaneously, right? Don't let any of them to wait for the other. We should let them run at the same time and eventually do a bit of operation to combine their results. And the rationale behind this design really comes from the virtual address. So as you remember, the translation between virtual and physical address happens only on the virtual page number part, right? They'll have the same page offset. So if my index to access the cache comes from the page offset, it's going to be the same for the virtual address and the physical address. So it's perfectly correct if I use the index that is part of the page offset to access the cache first. And this is only the indexing part of the cache, right? Remember, in a cache, if it's like a multi-way associative cache, we need to do both indexing and also tag comparison. And to do tag comparison, we do need to wait for the TLB, right, to get the physical tag that is the accurate physical address. So I'll first use the index to look up in the cache. the index is part of the page offset, and then I'll use the virtual page number to do the translation through the TLB. And we'll then compare the tag I got from the TLB with the tag in that cache set in the cache. Right? Tag comparison happens after I've accessed L1 and TLB simultaneously. Right? And depending on the comparison result, if it's a hit, data will just flow back to the core. If it's a miss, I'll access the main memory, right? The data memory. And potentially, if TLB is a miss, I also need to access the main memory, including the page table over there. The idea is, well, to sum it up, it's really we're taking advantage of this page offset that is not translated. It's not part of the translation, right? To, advance the cache indexing a little bit earlier. All right, that's the same slide. So here is like the numerical example based on the lecture slide. So I think here we have a 16-bit address. We have 4 kilobytes. Let me see. Well, it's not 4 kilobytes. It's 1, 2, 3, 7. We have 7 bits for the page number. I think it's like 2 kilobytes. Yeah.
Just to make sure I'm understanding this correctly, I guess. So the page offset contains both the set index and the block offset?
Yes.
Okay.
Interesting. So if you look at this picture, right, one way to split up the memory address is we have virtual page number, set index, and block offset. Virtual page number is the same as tag. The combination of set index and block offset will be the page offset. It's not always right, but this is the more common principle that we use in this class. You could also hypothetically use only a subset of the page offset for your indexing and block offset. You could. You're just wasting 1 bit from there, and eventually you'll use that bit as part of the tag. Right? The more easy way is to make sure the tag is the complete result from the translation, and the remaining bits becomes your in a cache accessing index. Right. So in this example, what you see, the TLB is sitting on the left, the cache is sitting on the right, right? They're sitting in parallel with each other. And we're using the upper bits, the virtual page number, to do the translation. At the same time, we're using the set index to pick that line from the cache. And once we have done both of these operations, we're just going to compare the tag in that cache line with the tag, which is also called physical page number from the TLB. And if it's a match, that means I do have the correct line in the cache, and I don't need to go to the main memory. I can just grab that data back into the original instruction requesting the memory access.
Oh, okay, I get it.
You got it?
Yeah. So, okay, so even if there's a hidden element, it could potentially be a longer.
Yes. Well, we really shouldn't call that a hit in L1. It's more like an index matching in L1. We still need to do tag matching to determine it's a hit or miss. All right, but I think you get the idea. All right, so these are everything I prepared for virtual memory. Any questions? All right, you remember what I said at the beginning? I have 20 slides for virtual memory. I have 1 for pipeline. So I think we're gonna end our discussion session a little bit earlier today. So, but before that, I'll just bring this pipelining and stalling example. This is the one we just seen, half an hour ago. And I just want to point out, remember, we have how many hazards in this example? Not just data hazard, like total hazard. or like 5 or 6, right? Some of them happen on the same instruction, so depending on how you count it. But you see, once we have elongated some of these instructions and delayed some of the F stages, what ended up happening is that for each register between the source and destination, or between its previous write and the subsequent read, those are all separated by at least a cycle, right? The read, or the one that is needing the data, doesn't happen until the cycle after, when we write the data. All right, and because of this nice staggering of the writes and reads, we don't have any hazards, right? Everything will be ready by the time when we eventually read it. All right. So I guess right between the write back and IF, that was originally a structural hazard, right? So remember, both of them are using the memory, right? And in this very simple architecture, we're going to have one memory. So that was a structural hazard. Now they're staggered. It's not a hazard anymore. Between 2 and 3, write back and the ID, originally it was a data hazard. Now again, I'm delaying instruction 3. So by the time I'm reading from the ID stage, it has already been written back the cycle before, so the data will be ready. Right? Between 1 and 3, originally, it was a structural hazard. Right? Write back and ID happens at the same time for the same address. We just assume that that is not allowed in the kind of simple architecture that we're analyzing. And now again, because of the delay of the third instruction, they're separated, so it's not a hazard anymore. And this analysis still applies to the remaining 3 dependencies. All right. But really, as Professor said, this is more for the hardcore architecture designers, whereas this class focused more on the software aspect. This is really out of our control, and we'll see in the next lecture how to deal with control hazards. And that is like the second question in the homework. All right. So these are everything I have for today. If you have any questions, let me know. Otherwise, class dismissed. All right. And thank you, Dennis, for joining us online. Okay, number of bits, like this one. Oh. You wanna tell us what you're thinking?
Kind of makes sense. I'll say something when I'm ready.
All right. Right, remember, block size becomes block offset, and here page size is correlated with the page offset. Right? Yeah. Log base 2 relationship.
Something I learned in 21 that you use throughout.
I
Block
see.
base 2, stealing the block base 2 data, cardinality data.
I see.
And included.
Well, I've heard that in CSE 30, some of these computer architecture topics are also covered.
I'm not sure.
Anyone has taken CSE 30? I see.
Did take another different system architecture class in college. It's kind of interesting how there's some overlap with this, a lot of different stuff. It's like half this and half like 1/4.
I see.
Okay, so the 12-bit page offset, that is from the 4 KB page size.
Yes.
Okay. So which is why there's 52-bit virtual page number. You just take 60 however many bit in the address minus however many bits in the offset.
Yes. Exactly.
Okay. So how does the 8 factor in? How does the 8-byte entry factor in here?
Each entry in the page table needs to store the translation, right? Those needs to store another 52-bit number. And typically we just round it up to the nearest multiple, like exponents of 2 number of bytes. So we're storing the 52-bit number in each entry, right? We're translating a 52-bit number. It's going to index into a cell, and the cell contains the result 52-bit number, physical page number. Well, even though we can do it in like 7 bits, we still just keep it as 8. We can do it in 7 bytes. Just for alignment purpose, we just keep everything as 8 bytes. Well, look at this. So 4-bit to do the lookup, and translations for 4 bits, right? 4-bit to 4-bit.
Okay.
So each of these cells needs to contain a 4-bit number.
Okay. Which is
right?
1
So
bit.
the size of this will be 16 times 4-bit.
Okay, sure.
Right?
Okay.
It's probably gonna be rounded up to 1 byte, since things are aligned by 1 byte.
Okay.
Let's make it a little bit easier to work with. And over here, each cell has a 52-bit number. Rounded up to 8 bytes.
Okay, makes sense.
Okay.
Would it be possible to add office hours or move yours to Friday or anything?
I'm thinking about it. I think well, should I move it to? Well, I can move. I have 2-hour office hours right now. That they are like Tuesday and Thursday before the lecture. I can move them to Friday and Saturday. Saturdays probably has to be like evening or so. Right? How does it sound?
That would be awesome. Yeah,
Yeah.
So I mentioned.
Yeah, I also recommend the other TA to move this office
Yeah,
out.
I mentioned that.
Time. Yes,
it's literally impossible to get him to help on the assignments because
Yes.
they're not there assigned. Yeah. I mean, he must get like no one in his office hours, right? Does he get anyone?
I don't know.
I assume he gets literally no one.
Yeah. Oh, well, yeah, we'll make some changes.
Awesome. Thank you.
All right, I'm gonna stop the screen share and stop the recording. And by the way, Blake, do you have any questions? Well, I saw there's only one guy online, but apparently there are at least 2 guys, Blake and Dennis. All right, yeah, bye. If not, I'm gonna stop recording. All right, see you.